I welcome you in my class. So today the topic is standard atmosphere. So we will discuss today, we will derive the atmospheric properties, relations, pressure, temperature and density, because ultimately aircraft has to fly in atmosphere only, right? So it is very important to know that where you are flying actually. In this case air has to fly in the atmosphere, right? So we should know that at what altitude the atmospheric property, how it is changing. For example, what is the pressure at a sea level and what is the pressure at a 10 kilometer, why the commercial aircraft has to fly at that altitude 11 and 10 kilometer, not at a sea level. So we have to understand our atmosphere, and then we have to decide at what altitude we used to fly. For example, like whether 5 kilometer is suitable or 4 kilometer is suitable or 11 kilometer is suitable, and sometime it is a requirement also. For example, like if you design any of the unmanned aircraft, so the requirement is you have to fly at a Leh Ladakh, where the altitude is more than compared to the sea level. So you should know the atmospheric property where it is. Sometimes the engine will work at a sea level, but engine will not work at that altitude because of this temperature difference, pressure difference and all. And even in the flight performance also we need to understand the density, because uh, in lift expression you have seen the density, right? So density will change with respect to the altitude and all. So density, pressure, temperature, considering these three property, we will derive the ratio. Like for example, if my altitude, if my pressure at this altitude is this much, what be the my pressure at that altitude? So, so we should start from the basics. So, for example, like we are dealing with here air only, right? So, consider this small element of air, which is having the unit area. Okay, so this length is also one, and this length is also one. So unit area, but height is dhg. Now hg is geometric altitude. So what is geometric altitude? Let's say you have a earth like this, the radius is this, and you are somewhere here. So from the center of this earth to this height is called absolute height, h. H is absolute height, and from the surface it is geometric height. So of course you can write absolute height is radius of earth plus geometric altitude. So radius of earth at equator is 6378 kilometer, right? So now so let's say P plus dP is the pressure for the top surfaces and P is a bottom surface, and this is just a small element of air having the pressure P plus dP as the top surface and P is a bottom surface. Why dP? Because there is a dH, right? So pressure will change. Okay, that is why I have denoted as a P plus dP. Okay, can you write this? What is mass basically? Rho into V, right? What is the volume? One into one into height dH only, right? Okay. If you multiply with the acceleration g, you will get mg equal to rho g dH, right? So this is nothing but the weight of this element itself. that will also act in a downward direction. This mg, okay. So you balance, but this element is not, it is stationary, right? It is not climbing or not descending. That means it is in equilibrium state, right? So upward force will be equal to the downward force. So what is the upward force? P plus dp and plus mg. Mg is what? Rho g dh. Okay. Force is just I have balanced the P plus dp into mg is acting downward and P is acting upward. So I have balanced. Okay. Now dp equal to minus rho g dh g. No doubt up to this, right? So simple, very in a very simplistic manner I have derived the same. Okay. Now you observe this. Now I will call this as equation 1. So now if I want to find out the P pressure, I have to integrate the same. This is equation 1. But since G is sitting here, which is also the function of altitude, okay. So as of now we cannot integrate this. So in order to solve this problem, one more altitude is defined, is called geopotential altitude. Okay, geopotential altitude. So here I am writing two equations. dp equal to minus rho g dhg, which we have already seen, and in this case we are writing dp equal to minus rho g naught dh, where h is the geopotential altitude. And now if you consider the geopotential altitude, you can replace g by g naught with the same pressure. Okay, dp and dp. So that is how the problem can be solved by defining the geopotential altitude. It is a fictitious altitude, and when you will see that what is the difference between geometric altitude and geopotential altitude, as long as you are going above the sea level. So with the common sense you can tell that at a sea level there is no difference between geometric altitude and geopotential altitude, because g value is 9.81. So g equal to g naught 9.81. But as long as you will increase the altitude, you will start seeing the difference. But even though at a 30 kilometer, 40 kilometer, the percentage change is less than 1% only. Okay. Now I will. So what you can do, then you should stabilize the relation between geopotential altitude and geometric altitude. Okay. So now I can write here from this equation 2 and equation 3, I can write g naught dh equal to g dhg, g into dhg. Okay. Now dh equal to g by g naught into dhg. And what is g by g naught? It is r divided by r plus hg. You have seen in the class 12 physics, right? Okay. dh. Okay. Now to make the integration simple, you can take r plus hg as a x, then dhg will be the dx, and if you replace this r plus hg here, you will get r divided by x square and dx. Okay, so you can integrate from 0 to h dh, and here 0 to hg take r square common and 1 by x square dx. Okay, so this will be the h, and this is r square, and this is minus 1 by x, and this is 0 into hg, and you can write here r square and minus 1 by x, x is r plus hg, and this you will write 0 into 0 to hg, right? Okay, r square, and this is 1 upon r plus hg, and here you will put hg equal to 0, you will get 1 by r and minus minus plus. Okay, so what you will get here, r square, and this is r plus hg, and r into r plus hg. So 1 r will get cancelled, r plus r minus r will get cancelled. So here you will get r hg divided by r plus hg. So this is the relation between geometric altitude and geopotential altitude. H equal to r hg divided by r plus hg. So this is the relation. So okay. So now we don't have any confusion between geopotential altitude and geometric altitude and absolute altitude. Okay. Now, why we have done this geometric and geopotential also I told you, because there is a problem of g. G is changing with the altitude. That is why we have defined the terms g naught considering the geopotential altitude. Okay. So now go back to this equation and equation 1, and we will derive the temperature ratio, pressure ratio at a different altitude. So we'll write dp equal to minus rho g naught g d. Okay, dp equal to minus rho g naught into dh. Okay, so now before going to this deriving the pressure, temperature and density at different altitude, you have to know that what is the atmosphere in a different altitude. For example, I can show you this diagram. You can see here on x-axis I am trying to show you the temperature, and y-axis, one y-axis, this is a pressure, and one is a geometric height. Okay, so you can see that the Mount Everest height is approximately 8.8 kilometer, and you can see troposphere, tropopause, stratosphere, stratopause, mesosphere, mesopause and thermos. So the terms pause here denotes temperature is not changing. Pause रुका हुआ है ना, तो from 0 to 11 kilometer your temperature is increasing. कितने altitude पर commercial aircraft flight करता है? Generally you will have seen the flight 35,000 feet. अब 35,000 feet को 3.28 से divide करो, देखो कितना आ रहा है. 35,000 feet को 3.2 से divide करो, कितना आ रहा है? 3.28 is a factor when you convert from the feet to kilometer. Okay, meter, and then multiply by, divide by 1000, you will get in the value in a kilometer. 3.28, 10.67 ना, 11 किलोमीटर. मतलब आप यहाँ कहीं ट्रोपोस्फीयर के बिल्कुल लगभग एंडिंग पॉइंट पे आप फ्लाई कर रहे हो. ठीक है, फिर उसके बाद आता ट्रोपोपास वेयर द टेम्परेचर इज कांस्टेंट. सो फ्रॉम दिस picture I am trying to give a little bit feel for the atmosphere. Like for example, how many layer the atmosphere is having, okay, and what are the ranges based on the altitude, like from this altitude to this altitude this layer will be active, and after this altitude another layer will become, okay. So that kind of feel I want to give you, that is why I have shown you this diagram, okay. So we'll go back to this expression again, dp equal to minus rho g into dh. So I want to find the, let's say for example I was at the sea level, but I want to find at the altitude or at pressure at 11 kilometer, okay. So what we will do, that means one value you are knowing, another value you want to find, okay. So let's develop the ratio of temperature, pressure ratio, temperature ratio and density ratio at two different altitude, okay. So you just divide by P here, P pressure, okay, and you know that P equal to rho RT, okay. So we'll check rho R is a guys constant. You know what is the R value for air? Air is having nitrogen and oxygen, right? So it will be roughly around 287, okay, in SI unit, okay. Rho G naught DH, here you make it as a P only, okay, and here you change, okay, rho RT, okay. Now rho and rho will get cancelled, and you will have dP by P equal to minus G naught RT into dH, okay. So now if I will integrate this point, okay, I will be able to easily integrate the left hand side, but again the right hand side dH is there, if I will get the H, but T is sitting here which is also changing with the altitude. So we have to define this temperature in terms of altitude, okay. So now you can define temperature at any altitude can be defined as a Ts sea level minus lambda into H, where lambda is a lapse rate. When and this lambda will change depending upon the altitude regimes. And what is the shape of this graph? Linear, non-linear, what is this? Linear, right? Linear, right, only, okay. And here with this lapse rate minus 6.5 Kelvin per kilometer, and in this stratosphere it will be minus 1, okay. Okay, so now this is the case. Now you can put uh, the T value here, minus G naught R Ts minus lambda H into dH, right, okay. You can integrate from sea level to some altitude P, okay. And now G naught constant, R is constant, so I will go with T sea level to some temperature, or this is 0, you are starting from sea level, right? So altitude will be 0 and some another altitude, fine, and this is Ts minus lambda H into dH. To simplify the integration, you can take Ts minus lambda H equal to X, and you can do the integration. So here you will get ln P2 by P1, and what is the integration of this? G naught lambda r ln T2 by Ts. Or instead of T2, you will say T by Ts. Okay, this is expression. When you integrate, minus lambda will come this side, minus minus will become plus G naught by lambda r, that is written here. Okay. Now this will be the log T. You apply the limit, you will be log T divided by Ts. That is how it is written here. Okay. Now you can write P Ps T Ts by G naught lambda r. Perfect, right? No doubt, right? Okay. Can you calculate what is G naught by lambda r is coming? By that time I will calculate what is the density ratio. This is the pressure ratio, right? So P equal to rho RT. So I can write P by Ps equal to rho by rho s into T by Ts. So I can write rho by rho s is P by Ps into T by Ts power minus 1. So what is P by Ps? T by Ts. This is G naught lambda r, and this is minus 1. So this is the expression of rho by rho naught or rho by rho s. So now we have found out the temperature ratio, pressure ratio, and density ratio. Temperature ratio easily you can find out from this expression, right? T equal to T naught plus lambda h. Okay. So you divide by Ts, you will get T by Ts equal to 1 minus lambda h divided by Ts. Okay. So easily you can find out the temperature ratio, no doubt. Okay. So now calculate me what is the G naught by lambda r is coming. So what is the value of G naught divided by lambda r? So okay, here is should be minus G naught by lambda r instead of plus G naught by lambda r, because if you take lambda equal to plus 6.5, so this sign will be the plus. Okay, ultimately this value should be positive. Okay, G naught by lambda r. So G naught is a acceleration due to gravity at sea level. So G value is 9.81 meter per second square, and lambda value is minus 6.5 Kelvin per kilometer, but we have to convert that in SI unit. So you may write minus 0.0065 Kelvin per meter, and R value is 287 joule per kg Kelvin. Okay. So you put this value and please tell me what is G naught by lambda r you are getting. So I have a calculator, I can also do the same. So 9.81 divided by 0.0065 divided by 287. Okay. So how much you are getting? 5.258643. After point you can remember as a mobile number. Everybody has known the mobile number, right? So you can remember as a mobile number also. See, 5.25864 you are getting. Okay.